So now what we'd like to do is use calculus to help us determine where a function's increasing and decreasing. In other words, what intervals it's increasing on and which intervals it's decreasing on. So if we have the picture drawn, it's clear. We could just point at it and know where the function's going up and where it's going down. But maybe we don't have a picture. We want a very precise way of determining where this function's going up and where it's going down over different parts of its domain. So let's just think about what we know about calculus to help us determine such a thing. Okay? In particular, think about this. We already can agree that over every point in this interval I1, the function's increasing. So it's going up. I'll draw a little arrow for increasing. Clearly, the function's decreasing on interval I2. So I'll draw a little arrow going down. And again, the function's increasing on interval I3, which goes out to infinity. Okay? So since we know that, let's just think about what we know about calculus. Well, think about it. What does the derivative tell us about a function? Remember that one of the things it tells us is the slope of the tangent line, the instantaneous rate of change at one point, right? Again, instantaneous. So think about it. If I look at I2 and I draw tangent lines at different points in this interval, look, here's one point. I'm going to draw the tangent line there. Here's another point. I'm going to draw the tangent line there. Here's another point. I'm going to draw the tangent line there. What can we say about all of these tangent lines? Well, again, the slope of the tangent line is the value of the derivative of the function, right, at a point. Well, notice that the slope of all of these lines is positive, right? So for every single point I choose in this interval I1, the slope of the tangent line at that point is clearly positive. Now, as we approach this point right here, where the function suddenly goes into a different interval, then notice how the slope is decreasing, definitely. It's flattening out. But regardless, every single point I choose in the interval I1, and I look at the tangent line there, that tangent line is going to have a positive slope. So remember, the slope of the tangent line and the derivative are one and the same. Therefore, we can use calculus. This means that, notice that for every point in I1, the derivative of my function at that point is positive, right? So I'll write that here. If the function is increasing everywhere, look, the derivative of my function at every single x in the interval I1 is going to be positive because it has a positive slope. Okay? And I should say for every x in I1. Okay? That is going to be one of the properties of all the points in this interval, a calculus property. That is, the derivative of the given function will be positive if the function is increasing on that interval. So for all those points, the derivative will be positive. Similarly, look, I'm going to do the same thing over here. Okay? Let me erase these lines. If I look in interval I2, choose any old point. There's a point. And then draw the slope of the tangent line, or draw the actual tangent line, right? There's the tangent line. Here's another one. Draw the tangent line. Here's another one. Draw the tangent line. Notice again a trend. Every single point I draw is going to have a tangent line that has a negative slope. Even if I draw this one right here, that's still negative. Although as we can see that as we're getting closer and closer to this sort of transition point between interval I2 and I3, the slope is flattening out again, right? But regardless, any single point I possibly can come up with in this interval I2 is going to have a tangent line that's going to have a negative slope. Okay? So just like what we came up with for all the property of all the points in interval I1, we can do the same thing for interval I2. That is, one of the properties of a function decreasing is that, in fact, the derivative of that function at every point in that interval is going to be negative. Okay? Because, again, the slope of the tangent line is negative. All right? So in particular, yes, the function is decreasing along that entire interval, but we just noticed something which we can use calculus to notice. Okay? That is, what we noticed is that the derivative of every point in that interval I2 is negative because the slope is negative. That's what we noticed. Okay? We noticed that property, that geometric property. And that means that it's true for every single point in the interval I2. So again, I can write for every x in interval I2. And similarly, we're going to find this for interval I3. that f derivative is going to be positive again for all the points in I3. And you can see this. Here's a point. I'll draw the slope line there. Oh, there it is. It's got a positive slope, right? And so the same thing for every x in I3. Right? So here we go. Now we've noticed something geometric, and this relates to calculus. So now we can use this to determine when a function's increasing and decreasing. We've got a definition already devised here. That is that a function is increasing on an interval if the derivative of that function is positive for every point in that interval, and similarly, a function is decreasing on an interval if the derivative is negative for every point in that interval. Okay, so now we've connected calculus with the concept of increasing and decreasing, just from looking at pictures. And this will be very useful if we don't know the picture of the function ahead of time. We don't have a picture. Okay? So let me write that down in a more compact form. So now let's summarize what we just came up with. Right? We saw this on a picture. So here's the theorem. Okay, this sort of summarizes everything. Suppose f is continuous on an interval I and differentiable at all interior points of I. Well, all that means is, well, we saw that from the picture. Continuous, right, we know what the definition of continuous means. Differentiable means, again, that there's no corner points or sudden jumps. And interior means sort of the open interval that's inside of I. So the punchline is that, in fact, if we satisfy these, that in particular, we see that if the derivative is positive at all interior points of I, all the points inside of the interval, all those points, then f is increasing on that interval I. Similarly, if f's derivative is negative at all points on interval, then the function is decreasing on that I. Okay, so here we've summarized all of that. And we came up with this by just looking at the picture of a function. We saw the function was going up and going down, and we just noted the geometric connection between the function going up and going down and slopes of tangent lines. Okay, and we know that that has something to do with calculus. So now we know there's a connection between calculus and the increasing and decreasing of a function.